Good afternoon, everybody. How are we doing today? My name is Charles Gibson, and I'm with the Michigan Science Center. I'd like to welcome you to our Science Spectacular webinar. And before we get started, I know that a couple more people, it looks like, are trickling in. So I wanted to go over just a few things as we sort of wait for our audience to build back up. So again, my name is Charles Gibson from the Michigan Science Center. ECHO is our distance learning program. That means that we can come to you virtually, and we can do this anytime, anywhere, with really almost any type of program. So today you're going to see some really fun demonstrations that we like to do here at the Science Center, and you'll actually be able to interact with us a little bit, ask questions about the demonstrations, and participate in some group polls so that we can see if you're paying attention. Just a real quick tour of Zoom. If you've never used Zoom before, if you hover your mouse sort of at the bottom or top of your page, you should be able to see a little bar pop up with some different icons. So video, participant list, Q&A, polls, etc. You won't need many things today. You can absolutely use the chat feature that's listed there, the Q&A section. So if you do have any questions, you can go ahead and shout those out to the group. I'll be monitoring those throughout the entire program. In fact, just so we're comfortable, if you wouldn't mind, just go ahead and use that chat feature. Send a little message about where you're viewing from and who's in your class. So we have Lindsay, hi from Michigan, hi from California. All right. So this will be cool. We've got a lot of interactive demonstrations that we're going to do with you today, ranging from, well, some chemistry, and then we'll observe some physical properties as well. And so if there's any time at all that you have a question about the demonstration that you're seeing, feel free to go ahead and throw it in that webinar chat box there, and we'll get to your questions in a fairly timely manner. So real quickly, a little bit more information about the Science Center. We are located here in Detroit, Michigan. So we'll go ahead and show you where that is. Let's see, one more slide here. We're located in Detroit, Michigan. So right there at the bottom of the thumb of Michigan. And so if you're located outside of Michigan, we welcome you. If you're located somewhere in Southeast Michigan, great. Maybe there's a chance you've been here before, or maybe you're somewhere in Northern Michigan. We think that's pretty great too. Of course, our ECHO distance learning program is brought to you by ITC. ITC is an energy transmission company, and they've been generous enough to sponsor both our traveling science and our ECHO distance learning programs. The Michigan Science Center, of course, has tons and tons of hands-on exhibits. So if you've never been here, we encourage you to come check it out. We've got 250 hands-on interactive exhibits that you can play with. We've got multiple theater spaces, like a planetarium that you see in that photo there. And we've also got an electricity theater and all sorts of really interactive stage presentations that we can do for you to make your day especially fun. So today, oops, excuse me, yeah, there we are on the map. We kind of pop over to that right about here as we kind of zoom right in. Yeah, I'm pretty good. There we go. Right in this little corner right here. That's where the Michigan Science. No, I'm way off, aren't I? I was looking at Warren. We're a little more this way. Haha. There's the Michigan Science Center. Yep, along there at Warren, the corner of John R. and Warren. So I'd like to pop back over to our webinar here. We've already learned that we've got some folks watching from California. We've got lots of schools here in Michigan. We welcome you all. Okay, so to kick things off, we're going to be talking a little bit about chemistry. Now, whenever we're doing chemistry experiments or demonstrations, we have to talk firstly about safety. So you notice that I've got a pair of safety goggles. I'm going to go ahead and pop these on. Might as well just leave these on throughout the entire presentation because I don't want to damage my eyes. So I'm going to keep those on. I've also got a pair of gloves. So these gloves are going to keep me nice and safe, keep my hands safe so that I don't end up hurting my hands there at all. Now the first thing that we want to do is we want to get you an understanding of what you know about chemistry. So I'm going to go ahead and launch a poll here with question number 1. So a poll should pop up on your screen there. And I'd like to go ahead and answer that question there. So which of these is an example of a chemical change Is it ice melting? Is it cutting an apple into different smaller slices? Or is it burning a piece of firewood? So go ahead and click on there, submit your vote, and we'll see how we did there at the end. All you got to do is hover over to your link there, seeing some votes come in. We're looking pretty good so far. Let's see what the rest of the group is joining. You can poll your students, kind of take a majority rule type answer here. Or you can have a little discussion afterward about why some of these other choices maybe seemed like a logical answer to this question. We've got almost everybody who voted. Give it about 10 more seconds. Somebody might be stumped on that last. What do we really think it might be? All right, we're going to go ahead, and I'm going to tell you that the answer is indeed the study of matter. Chemistry is the study of matter, and therefore when we're studying the changes of matter, an example of a chemical change would be something like burning a piece of firewood. So if we burn a piece of firewood, we're actually forming something entirely new. So an entirely new substance coming out of that, and that's where we can really study that matter. Now, speaking of combustion, I want to pop back over to our full screen video here just so you can see one of the demonstrations that I'm going to do for you. I have some spray bottles here, and each one of these spray bottles, even though they're different colored, has a different liquid inside of them. Each one of these liquids has a metal salt dissolved in them, a metal salt. So if you're familiar with something like sodium chloride that you might put on your French fries, these different metal salts are a little similar to that. We're not using sodium in this case. We're using things like copper, so copper chloride. Copper, of course, a metal that we see in pennies, in pipes, in wires. We have strontium chloride. Strontium is a metal that's used in something like a road flare. And then, of course, we have something like lithium chloride. And lithium is used in all sorts of our devices. So when we're using things like our iPads or our cell phones or other devices that need a big battery, we're often using a lithium-ion battery. And so I want to show you what it looks like when we burn some of these different flame salts, because we actually get to see how this chemical process kind of takes hold. So when we do combustion experiments here at the Science Center, we're talking about really three different things, three ingredients that go into combustion. That's fuel, heat, and oxygen. Fuel, heat, and oxygen, those three things form our little fire triangle. So I'm going to go ahead and turn on our portable Bunsen burner here, and I'll go ahead and ignite this. There we go. And you probably can see a nice bright burning flame there. I'll put my hand far enough behind it. You can see the blue of the flame. It's a very, very hot flame. And we're going to see what happens when we burn some of these different chemicals. So the first one that we're going to start with is our strontium chloride. So I'm going to go ahead and start to spray our strontium chloride. So everybody's ready in 3, 2, 1. Oh, so we get a nice kind of red, orange flame there. And remember, I told you that this was used in road flares. So that might give you a clue as to why or what color that was about to be. If it's used in road flares, get a nice bright red color. It's easy to see at night, things like that. Let's go ahead and take a look at our lithium chloride. So we'll see what color lithium burns when we spray it through our flame here. So here we go, our 3, 2, let me scoot that down so we don't get stuck. Here we go, 3, 2, 1. Oh, so a little bit different here. I don't know if you can see it quite as well on camera there, but it's a deeper red, almost a nice kind of a purple color from our lithium chloride there. It's sort of a nice one. And last but not least, our copper chloride. Or copper, you notice that the liquid here is a little bit of a different color. It's sort of cloudy, milky, you might call it. And so we're going to spray this through and see what color our copper chloride burns. Here we go. 3, 2, 1. Ah, how about that? Oh, I like to do it real slow like that. You guys see that nice, beautiful greenish blue color? So that copper chloride, you might notice that green color when the copper oxidizes or when it changes under a chemical reaction. If we leave copper outside for quite a long time, it actually does start to turn a green color like that. So this color that you see when it's oxidizing under a flame is very similar to that. I'll go ahead and just clean off my counter here, move some of these things aside as we continue to explore some of our different chemistry type experiments here. So we'll go back to our PowerPoint here. And so chemistry, of course, is the study of matter. When we're studying chemistry, we're studying how these chemicals are changing and other features just like that. So let's come on back here, make sure we're sharing, and there we go. Okay, which one of these is a chemical change? You guys did a great job with this one. You all selected, of course, burning a piece of firewood. Excellent job. Of course, as we're burning something, we're oxidizing it, and it is indeed changing to a new substance. So our next thing, this is a nice hazard sign that we use when we're dealing with flame experiments. Our next thing that we're going to be talking about is dry ice. Now, you can use the chat feature. Tell me if you've ever experimented with dry ice, if you've ever done any kind of dry ice demonstrations in your classroom. We are approaching Halloween time, so dry ice is extremely popular. That teachers bring it into the classroom. They make all sorts of great things with it. It makes this wonderful kind of fog that we'll see here in just a second. But if you've used dry ice before, you might know that there's a few additional safety precautions that we need to explore. So here's what we're gonna do. I'm gonna ask you another poll question. All right, water freezes at 32 degrees Fahrenheit. At what temperature will carbon dioxide, that's CO2, freeze under normal atmospheric conditions? All right, and this is dry ice. Dry ice is frozen carbon dioxide. So next poll we're going to launch is launching now. At what temperature will CO2 or dry ice freeze under normal atmospheric conditions? So go ahead and log your response there. Is it 0 degrees Fahrenheit? Is it negative 109 degrees Fahrenheit? Or is it negative 321 degrees Fahrenheit? All of those things sound really chilly. As we sort of enter the fall, as we enter winter here, it's going to get really, really chilly. Okay, so I was sort of divided there. I've got 3 responses in. Okay, hovering around there. Interesting. Oh, this is very, very interesting. So we have 5 people who have responded. Our majority answer, all 6 have responded. This is brilliant. This is really interesting. So I'm going to go ahead and end this poll. The majority here stated that water freezes under, or excuse me, carbon dioxide freezes at 321 degrees below 0 Fahrenheit. It is actually negative 109 degrees Fahrenheit. Now, negative 321 degrees Fahrenheit is another familiar temperature that we can see for another substance, and we'll come to that in just a little bit. So we're going to stop our share and explore a little bit about dry ice. Okay, so I've got some dry ice with me. Dry ice, as I've stated, is extremely cold. It's actually negative 109 degrees Fahrenheit. And so we're going to do a couple demonstrations with this so that you can see specifically how it behaves and how it sort of undergoes a transformation. So let's get a few of these things out of the way as we clear our lab table. I've got a nice cooler. Of course, that's where we're containing our liquid nitrogen. I've got a nice mixture of some other familiar chemicals that we'll begin to explore. And I'm going to need a piece of paper here for another really neat demonstration that we're going to do. So because it is negative 109 degrees Fahrenheit, of course, I need to wear some really heavy-duty gloves. These are going to keep my fingers nice and warm, protected from the really cold temperatures of our dry ice that we have inside of this cooler. So go ahead and pull out some of our dry ice, nice and squeaky dry ice. All right. Interestingly, dry ice is named because as dry ice because it is always dry. Sort of interesting. It doesn't actually melt. So unlike regular ice, dry ice does not actually melt. So you can sort of see this small cube-like or cylinder-like substance here. This is the dry ice. And I'm going to just breathe on this so you can see my warm breath interacting with the extremely cold dry ice. Here we go. You might notice there's a bunch of fog kind of coming off of that. So dry ice is known for being really sort of steamy and foggy like that. And we can do a number of really great demonstrations with our dry ice. You can see it right in front of my face there really nicely. So here's what we're going to do. I'm going to drop some here on the table. No worries about getting the table wet because, of course, it's dry ice and it's not going to melt. But I'm going to take a small amount of this dry ice and place it right into our bowl. And right away, you notice something. You might be able to hear a little bit of bubbling action. You hear a little bit of bubbling. You can actually see all of this fog kind of coming off of here, and it's really, really neat. Right? We have a nice little kind of Halloween-y type experiment here. So I'm going to add a few more pieces just so that we can get it to bubble up a little bit faster. We've got some nice warm water where we're creating that, that nice mixture. I'm going to pop off my gloves because I'm not any longer going to touch the dry ice, but what indeed I am going to touch is this mixture right here. This is soap and water. And so with this experiment, what we're going to do is we're going to see if we can get this nice and, oops, I spilled it, get this nice and damp here along the edges. We're going to see if we can create one giant bubble. This is a really fun type of demonstration experiment that you can try in your classroom. Pretty easy to do. I fold up a piece of paper so that we have a nice long strip like this. You can use a rag. You can use really anything like a long string. And I'm going to soak this all the way down into our soapy mixture just like this. Now when I pull this out, it's going to be all soapy and pretty wet. But what I'll do is I'll draw it across the top of our bowl here, and we'll see what happens, okay? So we'll go ahead and draw this out of here. We've got a nice soapy wet rag there. And then real quickly, before it gets too dry, I'm going to go ahead and just wipe it across just like so. That's perfect. So all of those bubbles now contained inside. I'm going to be real careful not to break this as I speak at it and as the air comes out of my mouth and kind of move this around. But we have a nice shiny orb now, and I can observe the little bubbles popping inside. I can see the different colors of the bubble on top there as it sort of swirls around. It's really interesting. And eventually, this is changing so much and it's becoming a gas, it might explode. So any second now, we might see that this bubble is going to burst and it's going to release all of that fog or all of that steam down onto the table. So we're waiting any moment now. Any moment. It's kind of the anticipation is building. You can see it sort of swaying back and forth. You kind of like give it a spell or something like that. All right. Well, this is a really good one. I wasn't expecting this. So any moment now, I see it's almost getting to the edge. It's slowing down just a tiny little bit. Let me know. Do you think I should pop it? Should I pop the bubble? All right, here we go. We'll see what happens first. I'm going to go in real slow with my finger right at the top. We'll see if we can pop it in 3, 2, 1. Wow. So it pops, all of that fog falls down to the side as it all gets released in that one instance, and we have a really cool kind of bubbly mixture as we continue to look at this really neat demonstration of a physical change. So we talked about chemical changes earlier. This is an example of a chemical change where we have the dry ice changing from a solid form into a gaseous form of our vapor, filling it up and of course taking up a lot more space. Now we can do this in another way with a coffee canister. So I'll take one of our containers here. You can get these, you save these from the grocery store. They're pretty handy for keeping things, but I'll show you what we like to do with them for our dry ice demonstration. So I'm going to take just a small amount of water from my graduated cylinder here, place it inside just like that, And then we're going to add, once again, our pieces of dry ice that I've saved here on my table. So we'll take these pieces, drop them inside. I can see some bubbling action taking place inside as the pressure starts to, or as the gas starts to fill up the rest of the container. And what I'm going to do is I'm going to take the lid, place it on top here, seal it down nice and tight, and we just wait, because it tends to release gas. As the gas, as it changes from a solid to a gas, the pressure, of course, builds, and you see a nice little explosion. Let's see if we can do that again. We can do this over and over and over. It never gets old. I can watch it. The pressure's building. There we go. One of my favorite demonstrations to do, especially with dry ice, and when we're talking about those chemical and physical changes. Now, when we're talking about dry ice is actually an acid. So carbon dioxide reacts with the moisture in the water, in the air, and we talk a little bit about acidity. So using my same graduated cylinder here, I'm going to add a little bit of what's called a pH indicator. This is universal indicator. Let's take just a very small amount of this and drop it inside here. And we'll go ahead, close this up, swirl this around so we have a nice green liquid. We have a nice green liquid there, okay? Now what I'm going to do is I'm going to add a piece of dry ice, right? Just a real small piece. And when it goes in there and it's starting to react with the moisture and it's starting to bubble around, I'm going to see what happens. Just a really small piece of that dry ice. And we're going to see what happens to the water and the acidity or the pH of this water as it reacts. So everybody watch carefully. In fact, I'm going to hold it up so you can see it in front of my coat here. So here we go. Drops inside. Watching it carefully. Already I'm starting to see a change. It switched to yellow. And as we're watching and as it continues to react, I'm seeing it change to orange. I'm seeing it start to change to almost a red color. Right? And if we let this react more and more and more, we would honestly get a nice deep red color, implying that this has become fairly acidic or almost like lemon juice. Because as this dry ice reacts with the water, it forms something called carbonic acid, which everybody knows about because carbonic acid is the acid that's inside of soda or pop. And that makes it, can damage your teeth and things like that. So that's why dentists often try to tell you to not drink so much pop. So see that color is getting nice and deeper there. And we are going to go back to our PowerPoint here and continue to explore kind of what else we might have for you. I have another poll. So with this other poll, it's going to lead us into our final demonstration here, and that's going to be using that really, really cold substance that I first told you about. So I'm going to go ahead and launch our poll, and our poll question now is, what gas comprises most of the air we breathe by volume? Is it hydrogen, nitrogen, oxygen, or carbon dioxide? Remember that carbon dioxide that we just used in solid form, of course, our dry ice. Our oxygen, of course, we need. Is it nitrogen? Is it hydrogen? All very good questions. Okay, so we're voting, getting that student feedback there. And we should be able to see what everybody's. So we have some interesting distribution here. Most of the air we breathe is made up of what gas? I'm still waiting on one more person to answer the poll. Let's see. Maybe we're still debating. Give you a couple more seconds. Is it hydrogen, nitrogen, oxygen, or carbon dioxide? We're going to end the poll with most of you, 60% saying oxygen, 20% saying nitrogen, and 20% saying carbon dioxide. The answer to this question is nitrogen. Nitrogen makes up nearly 78% of the air that we breathe by volume. Another 20% of that is oxygen. And of course, there are trace amounts of carbon dioxide and other gases as well. Hydrogen, not so much, though it is one of the most abundant gases in the universe. Okay, so my favorite part of the show, liquid nitrogen. Liquid nitrogen is 321 degrees below Fahrenheit. Liquid nitrogen is no doubt extremely cold. So we mentioned liquid nitrogen a little bit earlier on, of course, the 321 degrees below zero came up in our first poll. Liquid nitrogen is extremely cold and dangerous to the touch. However, nitrogen itself is, again, 78% of the air that we breathe. So we do have to wear gloves to be able to make sure that we use precaution. So I have some liquid nitrogen that I'd like to show you, and we'll do a couple real quick demonstrations with that. I have here a thermos, so something that you would keep your soup, your coffee, anything like that, your hot chocolate in. And then, of course, I have a much larger thermos. This is called a dewar. A dewar is a scientific vessel that we use to store our liquid nitrogen. This is the neck tube. The neck tube, again, insulates it and makes sure that this stays really cold. And I'm going to pour a little bit of liquid nitrogen out into my thermos here. So you might be able to see a whole lot of that fog as it's condensing the air vapor and the water vapor in the air into that nice cloud. It's bubbling all over the place. It's a very, very cold liquid. Beautiful. So I just want to remind you, if you have any questions or if anything has come up at all during the course of this show so far, feel free to throw it in that Q&A box or into our chat box there, and we will make sure that we get those questions answered for you at the end of the program. So now that I've got my liquid nitrogen stored inside of my thermos here, I want to do a demonstration with it, and I think what I need is another bowl. All right, so I have a bowl here, and lucky me, I've got a balloon too. All right, so I'm going to take this balloon and add a little bit of air to it. Now remember, the air that I exhale is still mostly nitrogen, maybe a little bit of oxygen in there, but it's also a larger amount now carbon dioxide, as my blood used that oxygen as I used it to respirate. So we'll get this blown up. Of course, unintentionally, I picked a balloon that almost matches the color of the wall there. And I want to know, what do you think is going to happen as I pour liquid nitrogen on top of this balloon? So, balloon goes into my bowl nicely just like that. And I'm going to go ahead and add some of this liquid nitrogen on top of the balloon. Is everybody ready? So here we go. I'll add our liquid nitrogen slowly but surely and observe carefully what begins to happen. Is anybody noticing what's happening? I'm wondering, is there a hole in my balloon now? Interesting. As I add the liquid nitrogen on top, as I cool the balloon down, it's seemingly starting to shrivel up, collapse into the bowl. Now this is very interesting. Got that inside. Oh, can you hear that? Sounds a little crunchy. So what I'm going to do is I'm going to pull the balloon back out. I want you to take a close look at the balloon. Don't look away so that we can see what actually started to happen. So here we go. Here's our balloon. Nice and crunchy. You hear that? But what do you notice is starting to happen? If I blow on it a little bit. You might notice that our balloon has kind of regained its original shape and size. Interesting. So what about all of the gas from my breath that will enter this balloon? Where did it all go? Well, again, liquid nitrogen is so cold that it actually condensed the breath that was inside of this balloon into a liquid. So you might notice this when you go outside on a really, really warm day, and you bring something like a nice ice cold water or a pop can or anything like that. And what you notice is that these little tiny droplets of water form on the outside of the glass. It doesn't mean there's a hole in your glass. It just means that it's so cold that it's condensing the moisture that's in the air. Just like we condensed the liquid that's inside, or the air, the gas that's inside of this balloon. It got smaller and smaller and smaller, molecules closer together, and eventually we had our breath condensed down to a liquid. Okay, so enough of the balloon. Next thing that we're going to do is we're going to observe our liquid nitrogen again inside of a test tube. So I have a test tube here, a glass test tube. I'm going to go ahead and pour some liquid nitrogen into here, and we will see what happens. So here we go. Liquid nitrogen goes inside. You might notice right away it is bubbling vigorously. Lots and lots of bubbles. I see lots and lots of steam and vapor kind of coming out of there. I'm going to add a small amount more because we want it nice and full for this next and final demonstration. All right, there we go. So the next thing that I'm going to do is I'm going to pull off one of my gloves. I have one more balloon, and I'm going to stretch this balloon on top of our test tube here. Okay, so as I kind of balance this up top here, we'll go ahead and see if we can stretch this right on top. In fact, I'm going to take my other glove off and real quickly and carefully stretch it over the top. Bam, just like that. Now, what do you notice already is happening? Well, as the gas continues to boil, it's boiling because it's taking up more space and it's changing from a liquid into a gas. As it's beginning to boil, we're seeing the balloon start to fill up. Now, this is interesting, and we could watch this happen for some time, but I think it'd be a little more interesting if we watched it happen much, much faster. So as my final demonstration, and thank you to you guys for tuning in today, we're going to dump the rest of the nitrogen into the balloon, and we are going to see what happens. So here we go. We'll dump it in just like that very quickly. We'll let this warm up just ever so slightly, and then we go ahead and we twist this, we pinch it off, and you might want to cover your ears. I'm certainly going to, because it is actually going to be very, very loud. Kind of swirl this around. The balloon gets bigger and bigger and bigger until eventually we end up with an explosion. Oh boy, we might have got lucky here. Let's see. There we go. That was pretty loud. And look at, now I have this octopus-like balloon kind of hanging off on the edge right here. All those latex, those fibers starting to string off. That was really impressive. That was super loud. I don't know. It was loud in your classroom if you had your volume turned up, but it was nice and loud in here. And we love good loud bangs like that here at the Science Center. That's how we often end most of our presentations. So furthermore, I want to thank you guys for joining me for this presentation today. Let's see if we had anything else that we needed to cover, any kind of questions at all. If you've got a question, go ahead, shoot it in that question box or that chat box right now, and we'll make sure that we get those questions answered. I do want to share with you also that if you are interested in doing a point-to-point or a virtual visit connection with just us and just your classroom, we can absolutely make that happen. We actually send you the materials to do a hands-on workshop, and we facilitate that with you and walk you through some demonstrations and some hands-on activities. There's some really great programs that you can check out on our website, on our Traveling Science and Echo Distance Learning page, and we'd love to have you do that. So a question from St. William, can you drink water that has dry ice in it? Well, this is an interesting question. because a lot of times during Halloween, we like to make spooky drinks by throwing a little bit of dry ice in there. There is absolutely a risk of that dry ice touching your lips, touching your tongue, and causing a frostbite burn. It could be very, very cold, so it could potentially be very dangerous. Now, if we think about the other chemical effect of that, as the dry ice interacted with the water, we created something called carbonic acid. Sounds pretty scary, sounds like something I wouldn't want to put in my body, but we do it all the time when we drink things like pop, Coca-Cola, or any other beverage that is carbonated. When we add that carbon dioxide to the drink, it reacts with the water and we create that carbonic acid. So yes and no. Yes and no. We definitely don't want that solid dry ice to touch our lips or our tongue or anything like that, because that could be potentially very hazardous. Any other questions? That was a great question from the group over at St. William. Well, if that is all the questions you guys had for me today, again, I want to thank you so much for watching. We're glad that you joined us. It was a pleasure presenting for you. Again, if you're interested at all in any of our upcoming webinars, please join us. They're often different demonstrations as we use them to fit other themes. And if you want to learn more information, you can do so just by logging in to our website right there. Again, thank you, everybody. Thanks for joining us. Please have a wonderful and safe weekend, and we hope to see you here at the Science Center if you can sometime soon. And if not, we'll see you virtually. Take care.